The hard part of the explicit formula is bounding the logarithmic derivative of the Riemann zeta function, which I'm going to denote like this. So thinking about the logarithmic derivative as a function, bounding this function in a strip containing the critical strip. So, maybe for the real part of the variable s between -1 and 2. So here I'm writing s is going to be sigma plus it. And this is difficult because the Riemann zeta function is mysterious in the critical strip. And as a reference for the for all of the explicit formula, but particularly for this part, I'm going to give Montgomery Vaughan they have a textbook multiplicative number theory or something like this, and it's going to be section 10. I think it's 10.2. And what they do there is they introduce what's called the Riemann xi function. So xi, I'm going to write it like this. So zeta with a line through it. So this is lowercase Greek letter xi. And it's defined to be 1/2 times s minus 1 times pi to the minus s over 2 gamma of s over 2 zeta of s. And the point of this definition is, well, maybe you recall that there is this completed version of the Riemann zeta function, pi to the minus s over 2 gamma of s over 2 zeta of s, and this satisfies the functional equation that lambda of s is equal to lambda of 1 minus s. So it's a very convenient way of writing the functional equation. You just sort of include these so-called gamma factors in front. And this completed zeta function, lambda, has poles at s equals 1, coming from the Riemann zeta function at s equals 1, and s equals 0, because, again, it's symmetric, and nowhere else. So this, I mean, really, the statement is that it's holomorphic on the entire complex plane, except for these two simple poles that it has. So the point of the Riemann xi function is that you're multiplying by s times s minus 1. So this s gets rid of the pole at 0, and this s minus 1 gets rid of the pole at 1. So this Riemann xi function is so-called, it's holomorphic on the entire complex plane. And then you have this 1/2 in front that's there. I don't know, that's how people define it. Arguably, this is really a minus 1/2 in front, because maybe you can think of this as an s times 1 minus s. That's natural from some perspectives, but of course it doesn't really matter. And so the Riemann xi function also is important because it preserves the symmetry s goes to 1 minus s, right? You can see that this part here, this is your completed zeta function, lambda, So that's symmetric under s goes to 1 minus s. And then, of course, this piece here is also symmetric under s goes to 1 minus s. So we can conclude that xi of s is equal to xi of 1 minus s. Okay. Or with a minus sign, right? Because when you replace s with 1 minus s, you have this minus sign. So this is just a function that people talk about, and in particular Montgomery-Vaughan talks about in the section 10.2. And they then introduce what's called a Hadamard product. So a Hadamard product is a relatively general thing in complex analysis, and you can check Montgomery-Vaughan 10.14 for and immediately before for exactly how this goes in this case, and how general this gets. But the idea is that the Riemann-Xi function has this expression as a product, which is going to be, let me check very quickly what it is. It's going to be 1/2 times e to the bs. Here b is just some constant, some is a real number. And then you have a product, and this is going to be over the zeros of the xi function. And here you have a 1 minus s over rho e to the s over rho. Let me double check to make sure. Yeah. And this is valid for all s, and here rho is all zeros of the xi function. And like I said, b is it's some real number, some constant. And this Hadamard product then allows us to look at the logarithmic derivative of the xi function. And by taking this logarithmic derivative, you can, it's straightforward to do. And then when we're interested in what we get for the Riemann zeta function, and for that I did the calculation just now. Hopefully I got it right, and I got from that section that the Riemann zeta function at s was equal to, here I'm going to write, so minus 1 plus the log of 2 pi plus 1 over s plus 2 minus 1 over s minus 1 plus the sum n from 1 to infinity of 1 over s plus 2n plus 2. So looking at this, maybe I probably should have taken this term and included it in the sum. But that's okay. Minus 1 over 2n. And then we also have the sum, again, over all zeros of the xi function. 1 over s minus rho plus 1 over rho. And so this is Montgomery-Vaughan, again, corollary 12.14, and with some additional ingredients from surrounding bits. One additional ingredient that's needed for this is Montgomery-Vaughan Appendix C, Formula 1, which gives this product expansion of the gamma function. Gamma is e to the minus, and now I'm going to write lowercase gamma to denote the Euler-Mascheroni constant. And then it's a product n from 1 to infinity of e to the s over n over 1 plus s over n. So here again, gamma is the Euler-Mascheroni constant, 0.577 ... So using this fact plus the definition of xi plus the Hadamard product, then you recover this expression for the logarithmic derivative of zeta. And this is what we're going to use to bound zeta in the critical strip, right? Because this was the objective that we had for this lecture. So what we end up getting is that in the range where the real part of S is between -1 and 2, and I'll allow equality here. There's the bound that zeta prime over zeta at S, so the logarithmic derivative of zeta, is equal to, and now we can go and we can look at what's going to be important as we go vertically up the critical strip. So this is going to be some constant, we don't care, this is going to be a constant. This sum, n from 1 to infinity, this is going to be about log of the imaginary part, right? And if you're close to the real axis, then maybe you have to have a little shift. So Montgomery and Vaughan say you have to add 4, so I'll trust them. So all of these terms end up contributing a log of t, right, where t is the imaginary part of S. We still have this 1 over s minus 1. Can't get too close to the pole at 1. And then we also have the sum over the zeros of the Riemann zeta function. So what we end up getting is that zeta prime over zeta is minus 1 over s minus 1 plus the sum over the zeros of the Riemann zeta function of 1 over s minus rho plus 1 over rho. And then the remainder is O of log, and then here I'm going to write the absolute value of the imaginary part, and then again, Montgomery and Vaughan say that I should have a plus 4 here, so, all right. Probably doesn't it doesn't really matter, but okay. And so this is the establishing this identity, or this approximation, is the major step in bounding the logarithmic derivative of zeta in the critical strip. Once we have this, then the rest is going to be not so difficult. Now, another observation that we're going to need is that zeta prime over zeta at 2 plus it is bounded, and for this you can just look at the series definition, maybe differentiate term by term, just all your series converge absolutely, so this is straightforward. And so we can take what we have up here, and we can take the difference with the value at 2 and get another approximation. So I realize here writing this, I think there might be a 1/2 here. I'm not sure. You can check, again, Montgomery and Vaughan for this. It's not going to end up mattering for our purposes, but I'll also write it here. I might have missed a 1/2 here, so double check. Okay, so because of this observation, what we can do is we can say, well, we can take the difference between zeta prime over zeta and at S and at sigma plus IT, and the difference, we look at the difference zeta prime or zeta at sigma plus IT minus zeta prime over zeta at 2 plus IT. And then this term is O of 1, so it's going to fit into our error term. And so this isn't going to... so this approximation is also going to be valid, but for this specific term here, we're going to make use of it to manipulate the sum into a way that we can understand analytically and bound more easily. So just looking at this difference, what we end up getting is minus 1 over s minus 1, so that is the term right here. And then for this term, I'm going to use the actual difference with 2 plus it substituted in here. So the difference of the 1 over rows all go away because I'm just, you get a 1 over row from both of these terms. And what you end up getting is plus the sum, again, there might be a 1/2 here, I'm not totally sure, of 1 over s minus rho, or maybe I should write it as, sigma plus it minus rho minus 2 plus it minus rho in the denominator. And so again, just taking this term and substituting in these two values of s and taking the difference. And we don't have a corresponding term here, of course, because the 2 plus it here is going to be still in this error term. So this is still plus O of log of the absolute value of the imaginary part plus 4. So for this, the reference I'll give, if you want to see it again in more detail, is Montgomery-Vaughan section 12. They do it towards the beginning of this section. Okay, so we have this identity. Maybe I will just check very quickly that whether or not there is, in fact, a 1/2. There is not. Okay. Great. And I can also take the opportunity to look up the specific thing. This is lemma 12.1. In fact, they say that here this is plus O of 1. I guess that's because the where we're getting the sum, maybe you get the same thing from both terms. It's not clear from exactly how I've set it up, that this is actually O of 1, but Montgomery-Vaughan says this is in fact O of 1. I will leave it as is, and hopefully we still get the same result. So we have this identity for zeta prime over zeta minus this, and like we said immediately above, this term is in fact O of 1, so we can conclude that just zeta prime over zeta at S, again for S between, with real part between minus 1 and 2, that this term alone is minus 1 over S minus 1 plus the sum over the zeros of the Riemann zeta function, 1 over S minus rho minus 1 over 2 plus IT minus rho plus O of log absolute value of the imaginary part plus 4. Okay. And with this approximation, we can really start bounding this as a function of t. So we want to know what happens when t is large. And here the result that Montgomery and Vaughan get is that this is this logarithmic derivative is at most the log of t all squared. But for our purposes, any power of any t to the epsilon would do. So let's get that, right? Let's get this upper bound on the size of this in t. And so the way to do this is, as the imaginary part goes to infinity, well, 1 over S minus 1, this term is really just telling you that whatever you're doing is not going to hold when you're near this pole, so don't be near that pole. And as long as you're not near that pole, then okay, this is we can ignore this term. And the tricky part is the sum over the zeros. So we're going to need another ingredient to bound the sum. So this is Montgomery-Vaughan, and let me check the exact theorem number. Montgomery-Vaughan theorem 10.13. So this theorem requires this notation that n of t is defined to be, so I'm going to write colon equals to mean defined to be. This is going to be, how exactly do they define it? Yeah. So this is the number of complex numbers rho such that zeta of rho equals 0. So these are zeros of the Riemann zeta function. And the real part of rho is strictly between 0 and 1. And the imaginary part of rho is strictly between 0 and t. So this uppercase t, this is the variable. So this is just the number of zeros that the Riemann zeta function has with imaginary part at most t, and counting only the ones with positive zeros. And the actual theorem is that n of t plus 1 minus n of t, so the number of zeros in this short window, this window of size 1, is at most, and then the bound they give is log of t plus 2. So they're saying, if you're looking really close to the real axis, then things might go wrong. So don't do that. So basically, what they're saying is that between t and t plus 1, the number of zeros you get with that imaginary part is at most log t. And this is going to be useful for bounding the sum over the zeros. Now, there's this caveat that if t or t plus 1 is exactly the value of the zero, of the imaginary part of the zero, so here I've just written strict inequality, but really you should count these with weight 1/2 if there's equality. So that's not going to matter for us, but that is what the actual theorem says. Okay. So we have this bound, and what that means is that the sum over the zeros, we're going to look at each piece individually and see how much we get from each piece. So the sum over the zeros of 1 over s minus rho minus 1 over 2 plus it minus rho, we can break up into a bunch of sums where we'll say sum n from 0 to infinity of the sum rho such that the imaginary part of rho minus our t, so here this t is the imaginary part of s, is in the interval between n and n plus 1. And maybe I'll do closed here. Okay. So we're just doing it chunk by chunk. And I don't know, if we happen to hit a 0 on the nose, maybe we can adjust it or something. We shouldn't worry too much about it. And then we still have the same things that we're summing. Okay, and now let's look at what happens for each of these individual terms. Well, for n equals 0, maybe we have to treat it a little bit differently. Here, we really might be like on top of one of the zeros. And that would mean that the logarithmic derivative of zeta would in fact have a pole, right? If s is exactly equal to rho, then yeah, we're getting 1 over 0, right? So the way to work that out is to say that the bound we're going to get is not a bound that is uniform for all s in this critical strip. We're going to have to avoid these poles. And but what we can say is that there are, at most, here I'm just going to write log t. So t is going to be assumed to be positive and sufficiently large. So there are at most log t zeros, zeros rho, such that s minus, here I think I can just write rho, s minus rho is less than 1. And what that means is that we can pick some s here so that the distance from our point to the nearest 0 is at most 1 over log t. So that means that there is say, an s prime such that s minus s prime is less than 1, so a point near s, such that this holds, and the distance from s prime to r0 is more than 1 over log t for all zeros rho. Right? Again, because there are log t of them in this little chunk of size 1, right? We've got t, and we've got t plus 1, and then we've got our zeros. And because there are log t zeros here, the spacing between them, there has to be somewhere where we can get at least a gap of 1 over log t. Okay? So what that means is that the n equals 0 part, well, we're not going to say that for any s it is bounded by log t, but we can say that the n equals 0 chunk is bounded by 1 over log t if there is this wiggle room. Okay. For the other ends, again, the ends here that I'm talking about are splitting up the sum into n chunks. Well, sorry, I should say this n equals 0 chunk is, I guess I should say it is log t over log t, because you do have log t zeros, who knows what happens, right? But it's bounded by a constant. And for the other ends, right, n from 1 to infinity, what we can do is we can look at this difference, and we can say so this is for any fixed n greater than 0, strictly greater than 0. We can look at this difference 1 over s minus rho minus 1 over 2 plus it minus rho. And again, here, remember our n is such that s minus the imaginary part of rho is in this interval between n and n plus 1. And it's a straightforward calculation to show that this difference is bounded by some constant times 1 over n squared. And here's where this taking the difference between the value of the Riemann zeta function at sigma plus it and the value of the Riemann zeta function at 2 plus it, that difference comes in really handy here, because the difference between these two things is 1 over n squared. But if we hadn't taken that difference and we had only gotten a 1 over s minus rho, then we would have had a 1 over n here, and then that would not give the sort of the desired behavior. So now we have to multiply by the number of zeros that we have in each chunk. So the sum over the rows such that s minus the imaginary part of rho is in this interval between n and n plus 1, again for n strictly, any fixed n strictly greater than 0, of s minus rho minus 1 over 2 plus it minus rho. And each individual term was 1 over n squared. There are about log t of these. We have to be maybe a little bit careful, but we end up getting, when done properly, let me get the equation number to give you the reference. When you do this properly, you end up getting there's no equation number. Okay, well, it's still lemma 12.1 in Montgomery-Vaughan, and you just end up getting log of the absolute value of t plus n plus a 4 for good luck divided by n squared. And then with this, what happens is, when we go back to what we were actually trying to estimate, we had the sum n from 0 to infinity, and so we have to sum this over n. So this implies that the value of the Riemann zeta function, the logarithmic derivative of the Riemann zeta function, at sigma plus it is at most, and then summing this over n, and looking at our estimate for n equals 0, what we end up getting is that this is at most log of the absolute value of the imaginary part plus 4 for good luck, and then the whole thing squared. And this is, let me get the theorem number, this is theorem, or lemma 12.2. And to be more precise, what the statement is that for any s, there is an s prime such that the distance between s and s prime is at most 1, and zeta prime over zeta of s prime is bounded by the log of the imaginary part squared. And that's lemma 12.2. So this was the most technical part of the explicit formula. In the previous lecture, we figured out a bound on the logarithmic derivative for the Riemann zeta function when we were in the complementary region, where the real part of s was either greater than 2 or less than minus 1, so the part where we can use the series definition or the functional equation, and that was relatively easy to bound. But bounding things in the critical strip, that was much more difficult, much more involved. We needed to use a Hadamard product and some identities and these relatively difficult facts about the number of zeros of the Riemann zeta function in any little window to bound these sums. So that's typically how it goes, that when you're in the critical strip, this kind of analysis is much more difficult, and usually your understanding of what's going on there is the limit for how good of a result you can get for whatever your application is.